Hello everyone, and welcome to this video, the 20th in the Kerr geodesics series. In this video we're going to look at how we can derive expressions for two of the components of the fall velocity, that is c dot and phi dot, of both massive and massless particles using two known constants of the motion, the energy and the angular momentum about the axis of rotation for a Kerr black hole. So we want to find the components of the fall velocity, which is the derivative with respect to some parameter lambda of the motion of a particle in the vicinity of a Kerr black hole. All right, so let's have a look at a bit of a diagram. So here's we've got our spinning Kerr black hole here, and we have some mass, but it could also be a massless particle. And what we want is, will that fit in there maybe? Yep. I hope my picture here isn't distracting you from the maths here and from the science. Anyway, so we have the fall velocity, dx mu d lambda, x mu are the coordinates of the object, of the particle, and the path of the particle is parameterized according to some parameter lambda, and its position will be given by x mu is x mu of lambda. And the derivative of each of these with respect to that parameter. Now, for a particle with mass, we can use the proper time tau, but I'm just going to use lambda here to represent both the case of mass and massless particles. And so x dot mu is dx mu d lambda, and what we want to find are these components here. We want expressions for these components here so that we could plot the path of the particle, at least in 3D space, or numerically solve and plot, but we'd like to be able to come up with the world line the particle follows. Tangent to this world line is the fall velocity and the components of which of this. And so this video and the next video is dedicated to finding these components. Now, in the past, in this Kerr geodesic series, we've dealt with motion in the equatorial plane. Now I want to generalize that to motion anywhere in the region around the Kerr black hole. Just remind ourselves the magnitude squared of the fall velocity is minus c squared. It's g mu nu, this object here, and the magnitude of the fall momentum squared is minus m squared c squared. Okay. Now, as I said, the motion is not restricted to the equatorial plane. We're looking about motion in general now. So we need to come up with expressions for ct dot, r dot, theta dot, and phi dot. And that would allow us to plot at least the spatial part of the motion of the particle. Now we can express the components of the fall momentum of massless particles, photons, gravitons, and maybe some neutrinos, in terms of the derivative of its rescaled coordinates x dot mu. So dropping the m's in here, dropping the m's, and just rescaling these coordinates such that each of the components of the fall momentum of a photon or something is expressed by, or each of these derivatives is expressed by the rescaled coordinate or the derivative of some rescaled coordinate. So for massless particles, we could have that fall momentum would have this form here. Okay, let's have a look now. So we need to remind ourselves. All right, a couple of things here. So we wish to find the equations of the geodesics followed by a free particle of mass m whose coordinates are given by this. So x mu is this, and lambda as an affine parameter. As I said earlier, for a particle with mass, we would use the proper time. So these geodesics have tangent vectors, as I pointed out in the previous slide, the red vector coming tangent to the world line here, or geodesics. We're dealing with freely falling particles, so that's why they're geodesics. Okay, now we can use the Euler-Lagrange equations, and starting back in the very first video of this series, that's what we did for the first couple of videos. We looked at the Euler-Lagrange equations and then decided we needed to restrict ourselves for motion in the equatorial plane because it was simpler to deal with that case. Now we're going to talk about motion anywhere. not just the equatorial plane. So we can use the Euler-Lagrange equations to derive the form of the geodesics for some Lagrangian L is T minus B. Now for a free particle, free particles following geodesics in space-time, for a free particle, Lagrangian is L equals T. There's no potential part here. Okay, so what we found, what we found is Lagrangian had this form, and when we did that for a free particle in the Kerr geometry, we got all this. And this is all the subject of the first video in this series. I'm not running through this now. Euler-Lagrange equations with these. And next one over. So starting with the first coordinate, x0 is t, so x dot of 0 is t dot. We put that Euler-Lagrange equations here for the t coordinate. This is what we've got. This part was 0. This dl dt was 0. And we end up with this dd lambda of this object here equal to 0. And that immediately, as you can see, gives us a first integral. So working through that, we divided through by 2, which brought this down here like this, because we had the minus 2 out there, dividing through. And we got this, gave us minus e, and so we could write, I'll just move that. We can express this total energy of the particle here, and this is the t component of momentum. So pt was minus the t component of momentum, the covariant component of the momentum in the t direction was p subscript t was minus e on c, or cpt was minus e, which is dl dt dot. That's what we found in the first video, and moving on to the next one. Okay, I might just hide that for a bit. All right. Now, so what we've got here now, the fourth component, x3 was phi, x dot of 3 was phi dot, and we found this again, dl d phi was 0. Over there, we're left with this. So a first integral of motion. So we found that the component of form momentum, the angular component of form momentum around that's the component of angular momentum around the axis of rotation, okay, is constant, it's conserved. And so p phi, component of the particle's form momentum, is conserved along geodesics. So p covariant component p phi is this object here is equal to this constant. And it just came, so these two t and phi components, they came out easily, very, very easily. First integral here, okay, and constant. But that didn't happen if you go to the second video in the series, in this Kerr geodesic series. That didn't happen. Okay, it wasn't as simple as that. All right. So we found in general dd lambda dl dx mu dot was 0. So dl dx dot mu is p mu, is a constant. That's what we found so far for those two components, not for the others. dl dt dot is cpt dot is minus e, and dl d phi dot is p subscript phi is h constant. Okay, so here's our, in general, each component of form momentum is this object here. And we can rearrange that, multiplying through by the inverse metric, and we can have mx dot mu is the inverse metric p nu. Now, in following videos, we found the following components. We found ct dot could be expressed by this, and phi dot could be expressed by this. Okay, the other two are unknown and will be the subject of the video that follows after this, in which we will deal with the Carter constant. But for the moment, let's have a look at these two here. And can we rewrite them? Well, a couple of things we need to do is make use of a few identities. This object here can be expressed by this. And to show you that this object is actually this object, I've included the algebra here. This object is expanding this out. Okay, delta is this object here, a squared plus r squared minus that. And expanding all this out, carrying out the algebra. I'm not going to go through in too much detail here, but you can take this out and have this here, back to that, then there's that. Now that sine squared can be replaced by 1 minus cos squared theta, the basic trigonometric identity, and when we expand it out we get this. Now minus a squared plus a squared will cancel, we're left with r squared plus a squared cos squared theta, which we recognise to be this rho squared. Okay, so we can write that as rho squared plus this object here. Multiplying through by 1 on rho squared, well, they cancel and we're left with this object, which is what we wanted to show up here. So that's our first identity, which will be useful in this video and the next. Next one, there's a few other things here. This one here can be shown to be this. I didn't provide that in this video, or the calculation, but you can verify that yourself if you want. One other thing, this can be replaced with this object here down the bottom. I'll just show you how I get that. Common denominator is c squared rho squared here. Put that over there. Expand that out. Again, replace cos squared with 1 minus sine squared theta. So when we do that, we end up with c squared a squared here. We end up with c squared r squared. And then we end up with minus 2 GMR here over c. So put that over c, because c squared times that cancel and we get this object here. So that looks like a delta. Minus c squared a squared on that. Next line down, this is delta, well-known identity. And here we go. And then we're left with delta minus a squared sine squared theta on rho squared. And we'll be using that in this video next. Let's keep going. All right, now let's start the first result. Remember we had CT dot was this object here. Well, what we're going to start doing now is multiply through by this. These two minuses cancel. We've got this object here for which we already have an identity. That is the E here. Now this result and the other one for phi dot was the subject of the earlier, it was the second video, first or second in the Kerr geodesics series. So how we arrived at CT dot and phi dot, just go back to those. Expanding out, here we go, expand across. Okay, we've seen this identity on the previous slide. Again, we have this, we can simplify all this, and we end up with something here which involves theta, r, and then these constants e and h. All right. And we multiply both sides by rho squared, we get rho squared CT dot is this object here. I'm going to do a similar thing now for the final coordinate phi dot, and then in the next video, I'm going to be looking at finding r dot and theta dot. So let's move on a bit. Okay, phi dot is this, as found earlier and found in the first and second videos in this series. Multiply out everything, put it in there, and as we do the algebra, multiplying through here, we end up with this object here. Again, just in the last step here is to multiply both sides by rho squared, so we get rho squared phi dot is all of this. All right, so we've got our second coordinate there. Now, in the next video, we will use the Hamilton-Jacobi equation to find another constant called the Carter constant. That's the subject of the next video. And the Carter constant will help us find expressions for r dot, theta dot as components of the motion of a particle in space-time. Now, remember the E constant, the energy E, and the H constant here allowed us to find neat expressions for the T dot component and the phi dot component, meaning dt d lambda and d phi d lambda. And we want to do a similar thing now for r dot, dr d lambda, and theta dot, d theta d lambda, but that will involve one more constant. So, and in the end, we'll actually turn out to have four constants. We'll have E, H, the Hamiltonian, and we will have a Carter constant. And that's the subject of the next video. So that's what I have here. So far, this is what we have, and we're going to find two more similar to this. And the next two expressions are going to have E, H, and R and theta in them as well. And that is for the next video. So that's what we found so far. So there were two constants of motion, E and H, which we found in the very first video in this series as a first integral from the Euler-Lagrange equations. And now what we want to do is, can we generate expressions for r dot and theta dot? And that's the subject of the next video. All right, thank you for that, everyone, and I'll see you in the next video, and we'll carry on here.